So in this video, we're going to look at the concept of an inductive relationship. This means that our nth term is the subject of the formula and it's given as some function of the n-1th term, and potentially it's also given as some function of n as well, the number of terms. So in the first problem, we're told find the next three terms of the sequence defined inductively by un is equal to un minus 1 plus 3 times n squared, where u1 is equal to 2. So let's use the formula that we're given then, and all we need to do is substitute in. So for u2, we've got u2 is equal to u of n minus 1, which is u1, which is 2, plus 3 times our n, and we're looking at the second term, so n is equal to 2, all squared. 2 squared is 4, times 3 is 12, plus 2, 14. For u3 then, u3 is equal to u of n minus 1, which is u2, which is 14, plus 3 times our n value, which as we're on the third term is 3, which we then need to square. 3 squared is 9, times 3 is 27, plus 14 is 41. For u4, u4 is equal to u of n minus 1, which is u3, which is 41, plus 3 times our n. We're on the fourth term, so n is equal to 4, which we need to square. 4 squared is 16, times 3 is 48, plus 41 gets us 89. So the next three terms are 14, 41 and 89. Moving on to problem 2 then, which is a little bit more complicated. For part A, we're told given that un equals n times n plus 2, find u3 and u5. So let's do this. For u3, our n value is 3, so all we need to do is substitute 3 into the formula. So we have 3 times 3 plus 2. 3 plus 2 is 5, times 3, 15. Similarly, for u5, n is equal to 5. So you have 5 times 5 plus 2. 5 plus 2 is 7, times 5 is equal to 35. So that's our solution then for part A. Part B says find un minus 1 and hence find an expression for un minus 1 where you simplify your answer. So let's start with finding an expression for un minus 1. Well, if we're looking for the n minus 1th term, all that means is every time we have an n, we're going to replace it with n minus 1. So we have n minus 1 times, in our brackets, n minus 1 plus 2. If we simplify this, we have n minus 1 times n minus 1 plus 2 gets us plus 1. And if we expand those brackets, we end up with n squared minus 1. So that's our expression for un minus 1. Moving on to the second part of B, we now want an expression for un minus 1. Well, our expression for un is n times n plus 2 minus, and our expression for un minus 1 is n squared minus 1. If we expand the brackets, we have n squared plus 2n. And if we take this minus into account on both terms, we have minus n squared plus 1. The n squareds cancel, leaving you with 2n plus 1, which is a linear expression. And that's our final part for un minus 1 in its simplified form. Moving on to part C then, it says hence write down an inductive definition for the series in terms of un minus 1. Well, that means that basically we want to make un the subject to the formula, and then we want to make it all in terms of un minus 1. So let's take our solution for part B of un minus 1. which is equal to 2n plus 1. If we move the un minus 1 to the other side, it becomes a plus. So un is equal to un minus 1 plus 2n plus 1. And this could be an inductive definition, but we want it all in terms of un minus 1. So we want to replace our n in terms of un minus 1. And to do this, we can move back to part B again, and we can look at our definition of un minus 1. So as un minus 1 is equal to n squared minus 1, we can say that n squared is equal to un minus 1 plus 1, and therefore n is equal to the square root of un minus 1 plus 1. Now that we've got that expression, we can substitute it in and say that un is equal to un minus 1 plus 2 times the square root of un minus 1 plus 1, all plus 1. And that is our inductive definition for the series in terms of un minus 1. And that's how we solve these two problems.